Okay, now we get to talk about capacitance. We're going to talk about electronic principles, capacitance, inductance, current flow in circuits, alternating current, definition of RF, and power calculations. Capacitance is the ability to store energy in an electrical field. That's called capacitance. The symbol for a capacitor is your wires coming through like this, and you've got this thing here that looks like it breaks the circuit. And what it is two plates that are separated by an insulator of some kind. It can be air, it can be mica, it can be paper, it can be ceramic. Any insulator between those two plates, and that forms a capacitor. Okay? And charges will build up on this capacitor. You'll have minus charges on one side, plus charges on the other, and that stores the energy in that electrical field. Okay? The ability to do that is called capacitance. Basic unit of capacitance is a farad. Now, you remember when we were talking about units, we were talking about microfarads and picofarads. We're talking about millionths and trillionths of a farad. That's because in the way all of this stuff figures out, a farad is an extremely large unit of capacitance. I doubt that unless you're working for the Hawaii Electric Company, I doubt that you will ever see a capacitor rated in farads. They'll all be in microfarads or picofarads. And because the farad is an extremely large unit of capacitance, but that's the one that fits into the basic scheme of the way the units all fit together. Okay, so we're going to be dealing with microfarads and picofarads. Any questions on that? Over here are a few photographs of various kinds of capacitors. They can come in a lot of different shapes and capacities, and with particular qualities that make them suitable for one purpose or another. Okay, in addition to being able to store energy in an electrical field, we can also store it in a magnetic field. And when we do that, it's called inductance. The ability to store energy in a magnetic field is called inductance. And an inductor is typically a coil in form. Here you see a coil of wire that's wrapped around here. You see a magnetic field that's produced by the flow of current in that coil. Okay, here's some different shapes of inductors. And depending on the frequency that you're dealing with, they can have a whole lot of turns to them, or they can have very few turns as the frequency gets higher. Okay? An inductor can be in the form of a transformer like this, where you have two inductors with a common core between them, which causes current that's flowing in one of the conductors to be induced into the other conductor, or inductor. Okay? Basic unit of inductance is called the Henry. The Henry. And again, it's an extremely large unit of inductance. You will probably, in all of your days of dealing with electronics, not deal with a unit larger than millihenries or thousandths of a henry. What is the unit of frequency? The unit of frequency is the hertz. Hertz is equal to 1 cycle per second. 1 cycle per second. And remember, the cycle is from one point on one wave to the same point on the next wave. Okay, 1 cycle. So if we take the positive going zero crossing here, and we go to the next positive zero crossing, then that would be 1 cycle. The number of those per second is 1 hertz. And again, that's an extremely low frequency. We don't deal too much in hertz. Well, we kind of do, because the power that comes out of the wall is 60 hertz or 60 cycles per second. But when we get into radio work, we're dealing in kilohertz, thousands of hertz, megahertz, and gigahertz. What is the abbreviation that refers to radio frequency signals of all types? It is RF, for radio frequency. What's the usual name for electromagnetic waves that travel through space? We call them radio waves. Electromagnetic waves that travel through space are called radio waves. Any questions on that? Now, how can we get a strange name like hertz for a unit, and Henry and farad and all of those kind of things for some of these electrical units? All of these names for the units come from the names of people who were pioneers in the the field of electronics and electricity and magnetics. So they seem strange, but that's where they come from. We have volt, volta, we have ampere, and so on. They're all people's names that have been applied to these various units. Oh, goody. Now we get to do some math, huh? Okay, what's the formula used to calculate electrical power in a DC circuit? Okay, the formula is power is equal to voltage, which is represented by the symbol E, multiplied by the current, represented by the symbol I. Okay, let's take a look at our pie chart. And you see that it truly is a pie chart because it says pi in there. Okay, and let me do something a little bit different here with my pointer if I can. Let's see. Let's use the spotlight for this. Okay. How much power is being used in a circuit when the applied voltage is 13.8 volts DC and the current is 10 amperes? Okay, now the way we use this pie chart is we have two things here that we know. We have volts that we know and we have current that we know. Okay, so we cover up the one we want to know, the one we don't know, and that tells us what to do with the others. Okay, so what this tells us is that we're going to multiply I times E to get P. Okay, if it was I that we wanted, we would divide P by E. If it was E that we wanted, we would divide P by I. So this is a division bar here, and this is a multiplication sign here. Okay, so in this case, we want to know power, so we multiply the other two together. Multiply the other two together. So if we have 13.8 volts and the current is 10 amperes, 13.8 times 10 is 138 watts. Okay, we multiply volts and amperes and we get watts. Okay, any questions on that? Okay, let me get back to my other thing here. Okay, how much power is being used in a circuit when the applied voltage is 12 volts DC and the current is 2.5 amperes? Again, we want to know the power, so we're going to cover up the P with our finger or our thumb, and we're going to say, we're going to find it by multiplying this times this. So we have 12 volts, the E is equal to 12, we have 2.5 amperes, the I is equal to 2.5. When we multiply 12 times 2.5, we get 30 watts. So the correct answer is 30 watts. Okay, here we're working in a different direction. How many amperes are flowing? So the thing we want to know is this one here, isn't it? Okay, so let's cover that up. When the applied voltage is 12 volts and the load is 120 watts, well, we know that we're going to divide the power by the voltage in order to get the amperes. So we're going to divide 120 by 12, and this will give us a current of 10 amperes. 10 amperes. Any questions on